let's go over the test we took here. This is test F, and it says determine where, let's see, first of all, the object's position, S of t, is in feet, so this is kind of like y, and this is kind of like x, time in seconds. And it says determine the average from 0.5 to 1.25. 0.5 time to 1.25. To find the average, you find the slope between those. We're finding the slope between an x of 0.25 and a y of 6 point, no, not 0.25, 0.5. 0.5, and the y value is 6.38, and the other point is at 1.25, and its y value is 10.36. So if I do the change in the y, I would take y2 minus y1. So it changed from 6.38 feet to 10.36 feet. That was the top, the feet. And the time changed from 0.5 to 1.25. So I take 1.25, x2 minus x1. And that's the time in seconds. So there's the units on my answer. So let's figure out what that works out to be. And to do this, I have a fraction, so I need to put my numerator in parentheses, 10.36 minus 6.38 divided by 1.25 minus 0.5. And the denominator needs to be in parentheses, and I forgot a parenthesis here. Insert a parenthesis. And so I get my answer to work out to be 5.31-ish, 0.6666, feet per second. So that's the velocity, average velocity. Then it says figure out the velocity, the derivative, at 1.25 using the central difference. Now this is an object that's moving, it's moving at 7. It might be curving up or curving down, but whatever it is, if we want to do the central difference theorem at 1.25, it says to do the points, not this one, but do just before and just after this one and find the slope of there. So if you have a curve and you're trying to find the slope there, you're using a point before and after, which is a pretty good approximation of the slope there. So that's the central difference theorem to find the slope at 1.25. So I'm going to use the point 1, 8, 1, 8, and 1.5, 14, 13. So the slope between these, y2 minus y1 over x2 minus x1. And this would also be change in the feet over change in the time. So the units will be that. Let's work those, do this calculation. So I've got to do parenthesis 14.13 minus 8.00 divided by open parenthesis 1.50 minus 1.00. And I get the central difference prediction for the slope at 1.25 is 12.26 feet per second. Now we want to do a linear approximation. So we're on the curve someplace, and if we go a little bit before 1.25, 1.23, we just use the line that we just got and put this into the equation of that line. Now, I want to talk about the equation of a line. For those of you who kind of rusty on it, and or those of you who in the book looked at the linear approximation formula. So you know that the slope, and we just talked about it, is y2 minus y1 over x2 minus x1. And slope is also f. The slope is the derivative of some function. It's okay. So this could also be said f prime is this, and that's the average velocity as we were doing. If I multiply both sides of this by those cancel, and I get what's called the point slope form of the equation of the line. It's y2 minus y1 equals m, or f prime, the slope, times x2 minus x1. So now, how many numbers are involved in this? Well, there's 1, 2, 3, 4, 5. If we know 2 points, like we did here, we can find the equation of a line by using them and come up with a slope, which we did. Or we can know the slope and one of the points, the x and y, and figure out the other x and y. Now, let's go ahead and find the equation of this line using this. All right, so we want to find it near 1.23. We know that the slope near 1.23 is 12.26. So we're going to put in this equation y2 minus y1 equals 12.26 times x2 minus x1. Now, to finish the equation, we need to know not only the slope, but the point near this. Well, that point is 1.25, and 1.25 is 10.36. So I can use this. I've used the slope, and I can use one point that I know the line goes through. This is supposed to be the tangent line at 1.25. So because that's the slope there. So we can use for y2 this, or y1. I'll make it y1, and I'll call this x1, and I come up with an equation that says y2 minus 10.36 equals 12.26 times x2 we don't know, just like we didn't know y2, minus x1, which we're calling 1.25. Now, the only thing we don't know is the other point. Well, the other point is the one we want to estimate when x is 1.23. So we put in 1.23. And if we do that, we get 12.26 parentheses 1.23 minus 1.25. And on this side of the equation, we get minus 0.2452. Now, to find out the y, the value that we're trying to estimate that goes with the 1.23, we would add this to the other side. So we'd add 10.36, and we get 10.1148. So at 1.23, we're estimating that we're going to get 10.1148. So that would be a place here, a little bit before we're thinking it's going to have a position of 10.1148 feet. And that's the units, and that's an answer. Now, that's using the point slope form. Now, the book uses the linear approximation, local linearization formula, and all they did is take the y minus y1 and add that amount to both sides. So they say that the y value will be the slope times x2, and we're trying to find the y2. We're trying to find at some other place, and so this is the x that goes with the other place minus the x1 plus y1. Now, if I put the numbers in this, we're trying to find the y that goes with a new place, 1.23. The place we already know is 1.25. The slope that we already know is the 12.26, and the going with the 1.25 that we know is the 10.36. And this will give us the approximate y that matches 1.23, the y2, for the x2, where this is x1 and this is the y1. So if I type this in to my calculator, I should get exactly the same answer. So I'm going to do that here. I'm going to go to 12.26 parentheses 1.23 minus 1.25 close parenthesis plus 10.36, and I get exactly the same answer. Now the book writes this as if you want to find a y value for some other x value close to some place, you use the slope near that place that you're trying to find it at. Remember, we were trying to find at 1.23. The slope near it, it's at 1.25, and we use that slope. We're trying to find the y value at a new place, and that's the new place. They call that x minus the location where we do know the slope, which is at 1.25, but I'll put x1 and x1 here, and plus y1. So they write the same thing, only using f prime for the m. They leave the subscript 2. The thing that you need to keep straight is that's y1, x1, and this is the y that goes with it for some point that we know. In this case, it's this point. And this is the slope near that point, which we did by central difference by taking these minus these and calculating that. Now, what I taught in the class before this was I just used the y equals mx plus b, thinking that might be easier for you. So we want to get an equation for the tangent line. And the tangent line, where we can do it, is at 1.25, where the y value is 10.36, and it has a slope there that we estimated with the central difference theorem of 12.26. So my equation for the tangent line, using this point and that slope, well, it would look like 12.26 x plus some b. And then to find b, we plug in the 1.25 for the x, take it times the slope, and plus b, it's supposed to come out to equal the y value. So let's figure out what the b is. So I'm going to multiply 1.25 times 12.26. And I get 15.325 plus b is supposed to equal 10.36. So I'll subtract that. So 10.36 minus the 15.325, and I get a b for my equation of negative 4.965. So I'm changing this to negative 4.965. So this is the equation of the tangent line, which if you were to take the 12.26 times the 1.25 and then add that, you should get that number. But we'll leave that alone. I won't show you more how those match up. This should be able to predict for any place close to 1.25, some y value. And that's what we're trying to find, the y value, using this line. And that's why it's called a linear approximation. So I want to find it at 1.23, which is close to 1.25, so I can be fairly assured that this is going to give me a reasonable answer. So the y that I would get is going to be 12.26 times 1.23, where we want to know it, minus the 4.965. So I'm going to type that in. 12.26 times 1.23 minus 4.965. And I did something incorrectly here. Oh, I didn't get 12.26. I missed the 1 for some reason. So let's bring this back. Oh, not that. And I need to go back over here and put a 1 in front of it. There. And we get the same answer that we've gotten before. That's a lot of explanation for this one. I showed you 3 different methods of doing it. You only need to know one way to do it. So I'm going to use the book method from now on, since that's what I saw a lot of you doing on the test instead of doing the y equals mx plus b method. So I'm going to use this formula for local linearization, finding a linear approximation of the function. Okay, I'm finally ready to go on to number 2. We have a bank balance. I could type this in as an equation, type this all in with putting 20 in for the t. So that would be 4150. Oops, you can't see it there. There. Parentheses 1.02, close parentheses, to the. Now, this calculator does pretty print. It goes up. If your calculator doesn't do that, you need to put the power in parentheses if it's more complicated than a single number. So minus 0.3 times 20 years later, and it gives a value of 3685.08. And it means that the balance in the bank uh, 20 years later. So that would be in 2010. That's 20 years later, the 1990. So there's the answer to A. Now I'm going to get it a different way. I'm just going to type the equation into y1, and I can go 4150 parentheses 1.02 close parentheses to the, and if you're doing it on a calculator that doesn't do this, again you have to cut parentheses. I'll put them just so you know. Minus 0.3 times, I'm going to put an x there for the variable. And now, since it's all in there, I can quit and I can go to my home screen and just say, okay, vars, y variables. Let me show you what I'm punching here. So, clear. Vars, the button right down here, y variables, y1 of 20 years. And it gives me that answer. It puts 20 into that function for the x that I put there. I could also do it this way. If I go to table set and have this on ask, I can then go to table, and I'll delete all those, and I can say, what is it at 20? And it'll say that number. Now you don't see the decimal place very well, but if you move over and on it, it shows you the complete number down here. So there's 3 ways to get 20 put in for the t. That's all it was necessary there. Now, determine b prime of 20. Now, we could do that with the limit definition of f of wherever we're looking, and in this case we're going for a equal 20, 20 plus h minus f of 20 over h, and let h go to 0. We could do central difference, which means we pick some place a little bit before, like we might do f of 19, a little bit after minus a little bit before. So f of 21 minus f of 19 over 21 minus 19, and it would give us a reasonable answer for this. Let's do those. So now to do this first one, I would go on the calculator, I would go to a new line and say I want to do f, which is y1, vars, y variables, function, y1, I want to do this in parentheses. Well, I'll go ahead and press enter, but I got to go back and insert a parenthesis. This is the numerator. y1 at 20 plus, and I could use h. On Desmos you can use h. On the calculator you can use h, but I can also use, in place of h, an x. So I'm going to do an x. Close parenthesis. That's f, y1, of the 20 plus h. I want to get it at 20, so I'm going to go 20 and a little off from it, minus f, which is vars, y variables, function, y1 at 20, close parentheses, divided by what I called x in here, so I'm putting in an x. And if I go back to that table now, it shows me what it's getting for a slope at 20. Well, that's not the slope at 20. That's just plugging 20 into that equation. But we don't want to put 20 in there. Remember, now x in this equation is supposed to be h, and h is supposed to be getting close to 0. So I want to put numbers close to 0, like 0.001 or minus 0.001. And you notice it gives me the same number from before or after, so that's got to be a pretty good guess for the slope at 20, negative 21.89. And the slope will be the change in y, which is the dollars in the bank, divided by the x is the time in years. So that's the slope using this one. Now let's do the central difference theorem. To do that, I can just go to my home screen and say y of 21, vars, y variables, function, y1 of 21, a little bit after, minus vars, y variables, function, y1 a little bit before, parentheses 19, and that has to be divided, but all of that has to be, so I should have put in parentheses, but I can also just calculate that, divided by 21 minus 19, which is 2, divided by 2, and I get same number, approximately. minus 21.89 dollars per year. Now I'm going to show you one more on here that I didn't show in class and haven't shown you yet. I have the equation here, and I have the ability to ask for what is the slope. Math, what is the derivative, the slope, and you're going to learn what this is in a sec, of y1 bars, y1 at 20. That's the shortcut on a calculator, and there's the same technology on Desmos. Now in Desmos, you can type this in. It'll give you h as a slider, but you can just say, go ahead and make it a slider, but then you can go in and just say, do h at 0.001, and go ahead and do h at negative 0.001. It'll give you this answer. And you can type this in. If you've typed f this in, or if you call this f of x, you can type that in. You can write, if you wrote it in as b of t, and put t in here, you can put b of 21 minus b of 19 over 21 minus 19 and get that. Or you can just, if you have that typed in, you can just say, you could type in f prime of 20 or b prime of 20, and it will give you this slope. So there's some shortcuts there that I'm giving you that I didn't give in class yet. We're going to get to what those are soon, but I'm just giving you a heads up. So if you're watching the video, you have a better way or a shorter way to do this. Write a sentence that explains the meaning of this. Well, we see that it's telling us that the amount of money in the balance in the bank is going down $21.89 every year. And it's important you say per year. All right, determine whether b double prime is positive, negative, or zero. That's whether it's, which way is it curved. So we would have to graph either the original function to know how it's curved, or the derivative, and if the derivative is increasing, it's concaved up. If the derivative is decreasing, it's concave down. We don't have an easy way to graph the derivative that I've shown you yet, so we'll just graph the original function, which is still in my calculator, and so I can push graph, and it's only going to do a small portion, but I think you can see that there's a slight curve up, which means concaved f, or the original function b of t, is concaved up, so b double prime is positive. Second derivative being positive means concaved up. And determine the equation of the tangent line at 20. Okay, we're going to use what we did up here. The book formula would be that the tangent line, which will be a function of b, but we'll just call it y, it'll be a function of time, will be the slope, and we figured out the slope is negative 21.89 9 times the time, any time later, minus the time we know specifically, 20, plus the y value that goes with that 20, and the y value that goes with 20 we did up here, so it's plus the 3685.08. Now, you can also do it in the y equals mx plus b or some other form. Okay, that was the majority of the points on the test. Page 2. Okay, let's start by doing the graphs. This graph is supposed to be the derivative. So the height of this graph, here it's -2, here it's 0, here it's 2, here it's 0, here it's -2, is telling me the slope of the f. And we're trying to draw f of x up here. So it has a negative slope, a 0 slope, a positive slope, and 0 slope, negative slope. So it has to go down, then it has to go up, and then it has to go down. So I'm going to start maybe here, and I need to go down with a slope of -2 to start with. Well, -2 is about like that. So I'm supposed to be going down like that, but by the time I get to -6, whoop, you can't see it here. By the time I get to -6, I'm got to be at a slope of 0. I don't know how far this goes down. Calc tool will know how far it goes down, but I'm just going to say I'm going to come down, and the slope is -1. So that's not as steep. It's more like this. So it's going to come down and be more like this. And then it's going to be 0 by -6. So there I've made it come down at -2, -1 for a slope, and then a 0 slope. -2, -1, 0. Now I got to go to a +1. So it's just going to kind of repeat what it was doing. Was a -1 about here, so we need about +1 about here. At 4, at -4 I should say, should be going up with a +1. And then that slope will gradually get steeper till it reaches a steepness of 2 by 2. So it's going to stay pretty much that slope of 1 and then get a little bit steeper until we reach 2. So it's 1 slowly increasing to 2. Then by 6, it goes back to a slope of 0. Well, 6 is here, and by then it's got to go back to 0, and it's kind of like the steepness here is the steepness here, but reversed. So it's going to be kind of like this parabola shape going back. And then it keeps making the same parabola, and it starts going to a -2 slope. So by the end, it should be going down at a slope of -2, which is kind of what I got right there. So that's what f of x looks like, ish. Now, key things to notice here. At -6, before it was going down because it had negative slope, and then after it's going up because it had positive slope. these values are negative, these are positive. Not looking at the slope of this line, I'm reading the values. -2, -1, 0, 1, 2. It's going from negative slopes to positive slopes. So when that happens, and there's a slope of 0, we're at a minimum. And here we're going from positive slopes to negative slopes. These are like 1 1/2 1/4 and 0. And now we've got -1/2, -1/4, -1 1/2, negative. So we're going negative. So we went from positive to negative, and right here there's a slope of 0, which means we went from a positive slope to a negative slope. We reached a max. So explain what the zeros, x-intercepts for this one, this is f prime again. When the x-intercepts are telling us that we have a min, if it's going from a negative slope to a positive slope, negative values to positive, or going from a positive to a negative, we're getting a max. If f prime equals 0 and changes from negative to positive, we have a minimum. For f of x. And if f prime of x is 0 here, and it changes from positive numbers to negative numbers, and then f of x has a max. Okay, now we're supposed to draw f double prime of x. So now we're not reading the values on here like we were to make that graph. We're reading this, we're estimating the slope of this and making those the values down here. All the way along here, it looks like it's going up 1 for 2. It has a positive 1/2 slope. Even though this is negative values, it's down. The slope is always plus 1/2. So the slope is always 1/2, clear up until -4. Then the slope goes from less than 1/2, goes down to a slope of 0. So it goes from here down to a slope of 0 by 2. And then all of a sudden it jumps to a -1/2. So there's a break in it, and it goes to a slope of -1/2 the rest of the way. So there should have been a gap there. Now, unfortunately, I made a graph where this changes pretty quickly, and when f double prime is 0, that's where the curvature could be changing. Well, the curvature changed quickly to no curvature at all there. It changed quickly here from no curvature to curve down, but it was a positive slope to a zero slope. So it's the second derivative wasn't zero, but here it hits zero but then changes. Usually when f double prime of x equals zero, we have a change. Oh, actually, it does work. I'm talking about the wrong one. This hits zero. There should be a change in curvature, not in f prime, but in f. So let's go back up here. This was 0 at 2. Look up here. The curvature is curved up. And by 2, it changes to curved down. So that's when f double prime equals 0, f changes curvature. Okay? That point is called an inflection point. Where the curvature changes, and it looks like it changes somewhere around in here. Now, according to this, it's going to happen right at 2. I may have been off a little bit here, may need to fix my curvature. All right, final question. Besides looking at f of x, looking at this one, what else is an indication that f of x is concave down from in the area from 6 to 10? Well, it's concave down there. It's actually concave for more. But from 6 to 10, we have, from 6 to 10, the second derivative is decreasing. And the first derivative is decreasing. It's decreasing from 2 to 10, and that's where it's curved down. So it's the first derivative is decreasing. Either f prime of x is decreasing. D-C-R-E-A-S-I-N-G. Or when this is decreasing, the second derivative is negative. And notice when this was positive, this was increasing, this was concaved up. When this is decreasing, this is negative, and it's concave down. That's what I'm looking for you to understand in E. All right. Now the simpler ones. Okay. To have a limit. So this is all about limits. So you need to know look at our note card if you need, that it has to have a left limit. It has to have a right-hand limit. And they've got to be equal. At -6, coming from the left, it looks like it's headed to about 2.5. Coming from the right, it looks like it's headed to about 2.5. So, are they equal? I would say looks pretty darn equal. And so we say, for the graph on the right, determine determine this if they exist. Well, it does. It's 2.5. If it didn't exist, explain why. Well, it exists. So all I have to do is give the number. Now determine this. So we're going to head towards 0. So moving towards 0 from the left, it looks like it's headed towards 2. From the right, it looks like it's headed towards 2. Are they equal? Yes. at this says just look for the one coming from the right. So we should be able to do that. Coming from the right, as we get close to 4, it's headed to a height of 2. We don't have to satisfy this just to do the left or right. Now on the last one, it says head to 4, the limit, so it has to have both of them. Well, from the left, it's headed to -1. To the right, it's headed towards 2. And are they equal? No. So there is no limit. And it says explain why. Because left and right limits are not equal. Okay, this section. Now we're supposed to determine if it's continuous at these x values. And if it's not, we got to explain why it's not. Okay, so then you have to remember your rules for continuous. It has to have a limit. It has to pass the test of that. It has to have a value. And if it passes both of those, then they have to be equal. So if it doesn't pass this, the equal is not going to be an issue. If it doesn't have a limit or if it doesn't have value, then they're not continuous. It doesn't get to the equal part. -6. At -6, it has a limit there. We already said it had a limit there of 2.5. So it has a limit. So if I made a little checklist here, let's say limit, value, and equal. On this, has a limit. Does it have a value? Yes, it's -2. So what it doesn't have are these two being equal. Has a value, has a limit, but they're not equal. So not continuous because limit does not equal value. Now they'll go to -3. At -3. -3. Does it have a limit? It looks like both sides point to the same place, so it has a limit. Does it have a value? Well, it looks like it's going to be at the same place, and so they're equal, so it's continuous. Then we're supposed to look at 0. Looks like it has a limit. Both of them go to the same place, about 3. Does it have a value? Well, there's not a hole, so it's got a value, and they look like they're equal, so it's continuous. All right, and then we're supposed to look at 4. Does it have a limit? Well, it failed. So I'm done. It does have a value. I don't need to check that. We know they're not equal, but it failed a prior test. No limit. So not continuous. Okay, now a lot of you talked about holes and values or something. I want you to use the math language. Talk about, is there a limit, is there a value, and are they equal? Now, is it differentiable at 0? Now there's only 2 things that have to happen for differentiability. Continuous, which has 3 things that has to happen. And and one of those three has three things that have to happen. So all these have to happen. All these have to happen to be continuous. And it must not be a cusp, a point. Can't be pointy. Can't have a sharp bend. So let's take a look at 0. Well, we've already decided it's continuous. And if we look up here at 0, it's continuous, but it has a cusp. So it is not differentiable because of the cusp. It is continuous, so it passed that part of the test, but it's not differentiable because of the cusp. Last page. Now I want you to use the limit definition. So you need, if you type f of x into your calculator, then you would have to do the limit as h approaches 0, if you use this definition, of f of 3 plus h minus f of 3 over h. Now, if you want to type it all in, you could say the limit as h approaches 0 of this with 3 plus h in for the x's, so 3 plus h sine of 3 plus h minus, now put in 3 for the x's, over h. So you can type this in, or you can type this into the Desmos or y1 on the calculator, and then make h get close to 0. Now you can use x's in the calculator, or you can use x's in Desmos, or you can put in h and it'll allow you to make h close to 0. But I'm going to type this in the calculator because that's the easiest to do here. So I have the equation of this kind of like this one here, except I need to change the 20 to 3's if I put the equation into y1. So I'm going to clear that one and type in x sine x. And when I'm in calc, I need to make sure my mode is in radians, and it is. Okay, so I've got x sine x, and I want to see what this looks like when my h, which I've replaced with x's in this equation, gets close to 0, and I'm at 3. So I need to come down here and change my 20 to 3. And my 20 to a 3. And now I got to look at this when x or h is close to 0. So second table. And close to 0 is these bottom two, and it looks like it's negative 2.83. Okay, so I need you to show me what you're setting up, the limit, and then you can do it on technology. Show the proper setup, either this or this. Okay. Now probably the easiest problem on the test. Usually the last problem is not the easiest one, but determine the equation of the tangent line. Well, I'm going to use the one the book then uses now, because that's what a lot of you are using. It's going to be y equals f prime of x. Well, it says and we're doing it at 5 because we're supposed to find the equation of the tangent line at 5. So I'm going to put in -6, parentheses, x minus an x we know, well, that's where we're looking at 5, plus the y that goes with that, well, that's 51. Now, let's go ahead and do the y equals mx plus b, just for we have y equals the slope at 5 is -6, x plus b, and the point, if I put in 5, I'm supposed to get 51. So I have 51 equals -6 times 5, -30 plus b. Add 30 and I get 81 is b. So the equation would be y equals 30, negative 6x plus 81, which is the same as this. If you take -6 times x, you get the -6x. -6 times -5 is 30 plus 51 is 81. So there is the equation of the tangent line. And the tangent line is going to give you a decent estimate for an x close to the 5.1. So all I have to do is put 5.1 into either of these equations. So let's doing the top one, -6 parentheses 5.1 minus 5 close parenthesis plus 51, and I get 50.4. If I put it in the other equation, -6 times 5 plus 81. Whoop. Oh, I'm supposed to put in 5.1. That's what it is. -6 times 5.1, because we're doing it at 5.1, plus 81, and now I get the same answer, 50.4. Okay. Had a negative slope, and I went a little bit further than 5, and so it should have been a little bit smaller than the 51, 50.4. And I should have shown my work here. And finally, I'll do that. -6 times 5.1 plus 81, or using that equation, -6 times 5.1 minus 5 plus 51. Either one of those works, gives you that. And then determine whether this value is expected to be an overestimate or an underestimate. Well, a tangent line depends on the curvature. If I have a graph that's curved this way and I make a tangent line, it's going to predict higher than the curve. Even if it's going downhill, it's going to be higher than the curve. If it's concaved up, the tangent line is going to have values that are below the curve, no matter where I make the tangent line. So it depends on the curvature. And fortunately, somebody told you the curvature is positive, which means it's concaved up. And so the line that we used is going to underestimate the value. Since concaved up, the estimate is lower. It's an underestimate. And that's it.